Finally. Now my guess is y'all know how to graph lines. You've probably been graphing lines for a long time. So if I said something like asking you to write the equation of a line passing through 1, -2, and 3, 5. No matter what kind of a line we're going to deal with, we always need to know two things. What are the two things that I need to know anytime we're talking about a line? And that is totally an option, right? Slope and where it crosses the y-axis. Another option is slope and any point at all, right? So most people, I find, most students are very familiar with and love our old friend, y = mx plus b. What I'm going to say is that y = mx plus b went to college and got more complicated. And what I hope I can shift your thinking towards is y minus y1 equals m times x minus x1. Now, the reason for that is that our point slope form, it turns out this is usually how we receive the information in a calculus context. We usually receive the information more of the time as a slope and a point, as opposed to a slope and specifically the y-intercept. So if I were trying to go through this problem, I can choose either of these 2 points. Doesn't matter. I'm going to choose the 3, 5 because anytime I can avoid negatives, I avoid negatives. So I'm going to choose that point over here. And I'm going to already start this as y minus 5 equals m times x minus 3. Then I just have to figure out the slope. In words, can anyone tell me how you usually think of the slope? Totally. Anyone else? Everyone's like a rise over run kind of person. I think change in y over change in x, because every time I'm like rise, run, I don't know, I could be running upstairs. It's confusing to me personally to use those words, but yes, absolutely. People talk rise over run or change in y over change in x. Doesn't matter which direction we subtract the points. It just matters that we keep them in the same order. So my slope here could look like 5 minus -2 over 3 minus 1. And I'm looking at 7/2 to stick in there. And then here's one of the cool things about calculus. I get to quit because this is the equation of a line. If you would prefer to write it in y = mx plus b, you absolutely can do some more algebra to rearrange that. But you don't have to. And one of my just sort of general pro tips as we make it through calculus this quarter is I am not someone who ever had extra time on a test. I was writing furiously till the very bitter end when someone ripped it out of my hand, which is to say that I had to really train myself to quit. So sometimes on problems, you just need to quit and move on to something else. So this is the equation of a line, and I'm going to walk away. But I did say that I wanted to talk about graphing today. And that's where, when I look at this, I'm like, yeah, I don't know, maybe having an y = mx plus b would make it easier to graph it. I am going to give you all a minute to graph it on your paper. If you want to rearrange it to y = mx plus b, by all means, go for it. Start here. Would you all, how many people would prefer for this to look like y = mx plus b first before we graph it? Okay, so that's maybe half of you. So that's enough that I'm gonna go ahead and do it. So if I were gonna get this to look like y equals mx plus b, I'm gonna start by distributing in that 7/2. Okay, my equal sign goes over there, but for some reason the 5 is gonna be underlined because that's how I roll. 7/2 of x minus, now when I distribute that in, I'm just going to take a moment to say, is anyone a psychology major? Oh, huh. Okay. I don't think I've ever had that happen in a 16A class. I always have a psychology major. That's okay. I was not a psychology major, but I think it'd be really interesting for someone to do a study because this weird thing happens when people see fractions. I swear there's like a special fraction part of your brain that for some people feels paralyzing. And then you start to get into this like panic mode of, I don't know how to do fractions. What do I do with the fractions? And so we're just going to confront that head on. And I'm going to let you know that I'm going to put a bunch of fractions in lots of the problems we do. As some sort of desensitization therapy or something. So when I take that 7/2 and I distribute it in, that 3 is secretly like a 3/1, which means I'm multiplying the numerators. So I'm going to have minus 21/2. Now, if I add that 5 over, so then I'm looking at y equals 7/2 of x minus 21/2 plus 5. Now I got to deal with more fractions. Now I need a common denominator because I'm trying to add some things. So that 5 is going to need to get multiplied creatively by 1, meaning 2/2, so that I end up with y is equal to 7/2 x minus 21, but plus 10, so minus 11/2. All of that is unnecessary work. It's totally fine if it's helpful for you, but it's unnecessary stuff to do on the page, and it took us time. But if that's what is going to help you get this thing graphed, that's also okay. Looking at this, I've got a positive slope and I've got a negative y-intercept. So I'm about to graph this calculus style. Oops, I missed. That is me graphing this thing calculus style. Now, I like to get all my points on problems. How many people like to get all their points on problems? So I have drawn, oh, not every hand went up. That's very interesting. Okay. So if you like getting all of your points on problems, we're going to have to label enough stuff on this to get full credit. What we do not have to do is draw a bunch of tick marks. What we do not have to do is figure out how to make this thing to scale. What we do need to do is label the x and y intercepts. And that's all we need to get full credit. So that y-intercept, we already know is going to be 0, negative 11/2. And that x-intercept over here, well, x-intercepts happen when y is equal to 0. So if I come back to this version of it, then plugging in 0 for y, that's going to get messy. I'm going to skip writing a step. I can see this next step. If y is 0, then that 11/2 is coming over to this side. So I'm going to skip to that step where I'm looking at 11/2 is equal to 7/2 of x. Because my denominator is 2 on both sides, I don't need to write it, which means 11 is equal to 7x. Or x is equal to 11 divided by 7. So there's kind of a lot going on in the statement of this question. But anytime we're being asked to write the equation of a line, I'm always looking for the same two things. I need a slope and I need a point. And I sort of hid both of those. But there are words in here that are giving me both a slope and a point. I promise not to make you talk. But stick your hand up if you know which word in that sentence is telling us a point. Keep your hand up if you're willing to talk. And I should have said this. I'm so bad with names, and I've had 18 months of cheating because names showed up for me on Zoom that I'm like really going to try to retrain myself. So I'm going to ask your name a lot. Please be patient with me. So let's see. Hi, I'm Sara, and you are? Gaia. What one word are you thinking of?
Through the origin, like passing through the origin.
Totally. So you took a phrase, and I'm going to steal one word from that phrase. When we say origin, what point do we mean? Totally. Now there's another word in there that is giving us some hints about the slope. And I'll take another hand because I really do want to learn names. So hi, I'm Sara, you are?
Isaiah.
Isaiah, what word are you looking at?
Parallel.
How many people were also thinking parallel? Awesome. Okay, so parallel. That's going to mean that I need the same slope as. I mentioned that I'm not always super quick. I certainly was not super quick on tests. The moment I know information, I want partial credit. Because if I don't have time to finish this problem, I get no points if I have nothing on the paper. But there's a possibility of partial credit if I rate something. So the moment that I know that point, I'm already thinking, I'm going to show that I know what the general equation of a line is by plugging that point into our y minus y1 equals m times x minus x1. I've showed that I know what the form for the equation of a line is, show that I know what to do with that origin statement, and now we just have to find the slope. So I will give you all a minute or so to come up with the slope. I gotta try that. Shall we get a slope going together? I'm not real big on mathy vocabulary, but it does occasionally show up in the context of homework and stuff. So I do want to point out what I have always thought was bizarre. This is called the standard form for the equation of a line. There's a reason that it's called the standard form, and it has to do with some linear algebra stuff. But the bottom line is nobody uses this form for the equation of a line. We're either dealing with y equals mx plus b or y minus y1 equals m times x minus x1. But this is called the standard form. I don't know about you, but I can't look at that and see the slope. So for me, if I'm going to find the slope of that line, I really do need it to say y equals mx plus b. So I'm going to shuffle things around. I guess I've got a negative 3y equals 12 minus 2x, subtracting the 2x from both sides, divide by a negative 3. I've got y equals 12 minus 2x, whole thing over negative 3, which means I've got y equals negative 4 plus 2/3 x. Some people can get to that 2/3 in their head. Totally fine if you get to that 2/3 in your head. I always worry for myself about making mistakes, so I do usually write that out. So I've got y minus 0 equals 2/3 x minus 0. We don't really have to write those zeros, so we can just say y equals 2/3 x. I can't remember what our actual 16A textbook calls them, but it might be parent graphs. So we've talked a little bit about lines, and in general, when we have lines, we've either got some sort of y equals mx plus b sort of form, or y minus y1 equals m times x minus x1. But the key for lines is that the powers on x and y are both 1. Well, if we take the power on x up a notch, then we're playing with parabolas. And when we talk about the parent graph for a parabola, we think about y equals x squared, which kind of looks like a U. And then we can think about how to shift and manipulate that parent graph. So if we're talking about parabolas, they come in lots of different forms. One form that we often use for parabolas, we might call the vertex form. So anything that looks like y equals a number times x minus a number squared plus another number. And we call this the vertex form because the vertex of that parabola is at h comma k. For example, if I said y equals negative 2 times x minus 3 squared plus 1, then the negative 2 out in front is telling me to flip this parabola vertically. So instead of being concave up like a U, it's concave down like a frown. And so this is going to flip it to be upside down. And then the vertex here would be at 3, 1. In the spirit of less work on the pre-calculus stuff so that we can focus our time on the calculus stuff as we move forward, that means that if I were to sketch a graph of this parabola, really the thing that I want to show here is where the vertex is and the fact that it's concave down. Now there's one little piece to this. If I'm trying to be pretty accurate with this, then it does kind of matter whether it's going to spread out and have a negative x-intercept and a positive x-intercept, or if both of those x-intercepts are going to be positive numbers. If I want to find x-intercepts, I'm looking for the place where y is equal to 0. So I'm going to quickly find the x-intercepts on this so that we've got a pretty accurate parabola graph. Again, I'm not going to worry about like tick marks or trying to scale this thing. I just want to be able to label those x-intercepts. Setting y equal to 0. I can subtract that 1 over and divide by -2. So doing those two steps at once, I would end up with a positive 1/2 is equal to x minus 3 squared. Now we have come to a point where I need to like take a little side note for a second because we're about to take a square root. Side note. The square root of 16 is 4. It is not plus or minus 4. Mathematicians had to decide on some sort of convention. And the convention that they decided on was when we take a square root, the result of that square root is going to be a positive number. The square root of 9 is 3. However, if what I'm being asked to do is solve something that looked like x squared is equal to 16, the solutions to this equation include both positive 4 and negative 4. So when we take the square root of two sides of an equation, we generally compensate for that by noting that we're going to need the positive and the negative part of the square root. The like long play version to do that, if I were trying to solve something like this, would actually be to subtract that 16 over so that I have a 0 so that I can get this factored and see that indeed I do have two answers. X could be positive 4 or negative 4. But we're not going to do that with this problem. We're just going to note that when we take the square root of both sides, because it's in the context of solving for that x minus 3 squared piece, we're going to give that a plus or minus square root of 1/2. So here I am looking at plus or minus square root of 1/2 is equal to x minus 3. That means that I'm looking at x is equal to 3 plus or minus the square root of 1/2. I don't know whether this came up in your first lecture or not, or if it's maybe hiding somewhere in Canvas for you all. In general, UC Davis is not a calculator campus when it comes to quizzes and exams. What that, oh yeah.
I might have just misunderstood, but wouldn't in the black, wouldn't that 1/2 be negative?
Got it. I did two steps at once in my head, and I apologize for that. I subtracted the 1 over and then divided by a -2. So I ended up with -1 divided by -2.
Why would you divide it and then not just add the 2 to that?
Totally. So the issue here is our invisible order of operations. So that -2 has an invisible multiplication with the parentheses next to it. So that means if I'm going to move it, I've got to move it by dividing. Yeah, totally. Back to my calculator pitch. Did it come up in class for either of you? I didn't see anything on Babson's website specifically talking about it, but I'm also not in Canvas. Is he using both the website and Canvas? Neither of them added me to Canvas. Okay, I was like, he sent me a link to the website, so I just assumed that's all there was. Okay, cool. So I don't see any information on there about using calculators. Typically at UC Davis for calculus classes, we do not allow calculators, which means two things. One, the numbers will stay pretty simple and there is not an expectation that you simplify them, which I think is good. But it does mean that if we get down to here, you have to have sort of enough number sense to be able to say, well, the square root of 1/2 is small. It's certainly smaller than 3. So if I have 3 plus the square root of 1/2 and 3 minus the square root of 1/2, those are both going to be positive numbers. And I can finish my parabola off. And then just label it as 3 plus the square root of 1/2 comma 0. Gosh, this is getting tight. and 3 minus the square root of 1/2, comma 0. Absolute value graphs look like a V. And if I take that parent graph of y equals absolute value of x, this is just a V that touches the origin and bounces off on either side. And in general, when I have some sort of parent graph, if I add or subtract something where the x is kind of in parentheses, that's going to shift us left or right. And if I add or subtract something off the end of it, then that's going to shift us up and down. So when we talk about absolute value graphs, we also talk about a vertex. So that pointy part at the bottom, we sometimes call a vertex. Sometimes I've heard it referred to as a cusp. Either one works. So if I were to take this and shift it by saying something like absolute value of x plus 2 minus 4, that plus 2 part is saying to shift 2 to the left. And the minus 4 on the back end is saying to shift down 4. The other way to think about this is to just figure out where that vertex point is. And kind of similar to what happens when we've got parabolas, that x value of the vertex is going to be whatever makes this part, I know it's not in parentheses, it's in absolute value, but whatever makes that part equal to 0. So in this case, plugging in -2 for x is what would make the absolute value part 0. Then we think about, okay, if x is -2 and we plug that back in, what do we get for a y value? So if I plug that -2 in, -2 plus 2 is 0. That was the whole point. 0 minus 4 is -4. By setting the part in, I know they're not parentheses or absolute value, but setting that part equal to 0. Yeah. And that green isn't showing up super well, so I'm going to quit using it. So I can think about taking this graph and I can think about it in terms of shifting. So I know that this says shift 2 to the left. So I'd be like moving 2 to the left and then down 4. So my new vertex would be down here at -2, -4. And then we could draw our V out.
In order to get that x point, do you just set the y and the x to 0, and then that's for sure going to be your next person?
So maybe, but let me see if I followed what you meant. So to get the x value, I take whatever is inside of the absolute value. So I'm taking that like absolute value of x plus 2 part and setting that equal to 0. So x plus 2 would be 0, and then I can subtract 2 from both sides to get that x is equal to -2. Then I plug that back in to get the y value. Idea that if I have two numbers, one way to find the midpoint is to take their average or to add them up and divide by 2. And when we're finding the midpoint, we're just doing that twice. We're doing it once for the x values and once for the y values. It's not terribly exciting. So the x value for my midpoint in this case would look like 2 plus 7 divided by 2. And the y value for my midpoint would look like 5 plus 11 divided by 2. Cool, I'm done. Alternately, right, like you could simplify those fractions and call that 9/2, and 5 and 11 is 16. 16 divided by 2 is 8. That's fine. I don't know how to make a midpoint problem harder than that, but our textbook does. And really the way that our textbook makes midpoint problems look harder is by kind of trying to hide a piece of information in there, right? So maybe it might say something like, -1, 2 is the midpoint of 0, 4, and what other point? Zero comma 4 was supposed to be one of my points. So 0, 1, 2, 3, 4. And then this midpoint is at -1, 2. 1 up 2. And I can kind of visually see that if I just connected the line there, that because I did draw this to scale, I can see that that's looking like -2, 0. Now it's a little bit hard to do that in 2 dimensions all at once, but if we simplified that and just looked at the X values separately from the Y values, if I looked at the X values, and here again, I'm kind of thinking about a number line, one of my points is 0. The midpoint is at -1, which means that is a distance of 1. And if I move 1 in the other direction, I would get to -2. And if we did the same thing in the Y for the Y values, and I know I drew that horizontally, oh well. I'm looking at a 4, and then the midpoint is over here at 2. So that's a distance of 2. And if I moved 2 more in this direction, I would be at 0. Five, and I've got the point 7, 11. Well, 7 should be further to the right than 2, and 11 should be further up than 5. So here's my other point, 7, 11. And my point about the hypotenuse and then the legs of the right triangle, if I connect these in here, that's really the distance that we're looking for. And one option is to imagine for ourselves a right triangle where the distance we're looking for is the hypotenuse. Then I can think about what's this side of that right triangle look like? Well, I started at a height of 5 and I ended up at a height of 11, which means this side is a 6. And do the same in the X direction to say I started at an X value of 2, I ended up at an X value of 7. So that's a change in 5. So I'm looking at this triangle with sides of 6 and 5 and asking myself, what is that third side? Back to Pythagorean theorem, 5 squared plus 6 squared would need to equal c squared. Five squared is 25, 6 squared is 36. 25 and 36 sounds like 61. And I mentioned before on my little side note that when you're solving for something and you end up taking the square root, we should think about the positive and the negative. This is a case where I'm not going to do that because there's context to the problem. I was asked for a distance. So that distance is a positive number. So when I get this, I'm going to say that that distance is the square root of 61. Now we can also write this in a formula sort of way. And as a formula, that distance formula is going to look like we're finding the change in the two x values, squaring that, finding the change in the two y values, squaring that, and then taking the square root of the whole thing. Mechanically, those are the steps that we went through, and the formula just puts it all into one thing. So that is our distance. One thing to keep in mind in terms of Pythagorean theorem, and this goes back to the fact that Davis is not a calculator campus for calculus stuff. There are some nice sets of what we call Pythagorean triples. And when we see those in a problem, your instructors think that you are not going to have to work too hard to come up with the numbers. So two of our common Pythagorean triples. Yeah, I guess I'll just squeeze them in over here. Two of our common Pythagorean triples are a 3, 4, 5 triangle. And that means any multiple of those sides. So if I scale each of those sides by 2, then a 6, 8, 10 triangle is a Pythagorean triple. If I scale all of the sides by 20, then a 60, 80, 100 triangle is a Pythagorean triple. The other one that comes up still fairly often is a 5, 12, 13. So I'm just planting the seed now that if you're doing one of these problems and you've got sides of 5 and 12, 13 is that third side.